Welcome to the second video for buckling, uh, meant to be viewed on April 22nd. And this one, we'll go through the Euler-Buckler equation and the sort of conclusion of what that means for us. Now let's consider a more realistic column, one that was originally maybe shaped like that, but which is deflected now as it's been loaded into a shape like that, where we've got some deflection because we've applied a load at the top of P, and of course a load at the bottom also of P, because we need to maintain static equilibrium. And let's look at a point right there. We'll call it Q. This is A. This is B. So if we look at just Q, let's zoom in on that. Our forces acting on it are going to include, obviously, that P is still there because this is point A, and we're going to have an internal force in the y direction of P at Q. But we're also going to have formed a moment right here. Right, so these right here, there's an offset, so they're going to cause a moment in that direction. We're going to need to exert a moment to resist it. So this is point Q, and that's point A. Alright, so we've got this shape. We know what the moment is based on the fact that we know what P is, or rather we're going to deal with it as P. And then we've also got our deflection, which we're calling Y. I know it's deflection in the horizontal direction. Don't let that confuse you. We're still going to consider X to be the direction along the axis of the column. Okay, so even though right now we're drawing it with the X direction going vertically and the Y direction going in the horizontal direction, don't let that confuse you. You know, like using sine and cosine. Some of you seem to think that sine just always means the vertical component. It don't. Be careful with this, because y is whatever direction you've chosen to make it. So we've got that, which means that we know that the moment at this point, I guess it's a function of x. Sure, why not? Can be, because it's going to change as we move along here. Is going to be equal to the force P that we have applied times this distance y, which is, a function of x. We also know that the deflection y is a function of the moment, right? The moment diagram, the moment function, we're going to integrate that to get our rotation, then we'll integrate that again to get our deflection. So we can say that the moment is definitely equal to the derivative, the second derivative, I should say, of the function y. So we've got two of those. We can now set them equal to each other. Also remember that, let's not forget to put the second moment of inertia and the Young's modulus in there. So we can say that 0 is going to be equal to this the second derivative of the deflection function plus p times y. We'll just divide that one by ei. That should be a negative sign right there. So we've got that. This is a differential equation. For those of you who have taken that, that should be hopefully almost all of you. But don't worry. You might be shouting at your computer right now, well, hold on there, Dr. Butters. That isn't a requirement for this class, and you're right. So I'm not going to make you solve this equation as a differential equation. I'll just give you the solution given to us by Euler. So this is going to give us Euler's buckling load, or Euler, some people pronounce it, I believe incorrectly. So it's going to give us that the critical load is equal to pi squared times the Young's modulus and the second moment of inertia divided by the length squared, which is going to give us a value for the critical stress that is going to be, well, that divided by A, right? And that's going to be, well, pi squared times the Young's modulus. We can switch this into using the radius of gyration. So A times the radius of gyration squared divided by, well, L squared, and that A is still there. Then we can cancel those two out, and we end up with pi squared, the Young's modulus times the radius of gyration squared over L squared. So this is a new value to limit our allowable stresses. When we're looking at our allowable stresses, now we have four things, and we're going to plot them. Let's plot them. We've got the stress, and then we've got L over R. That's the slenderness ratio, and it's what we use when we're sort of picking out columns. If we have a very low slenderness ratio, then the limiting factor as far as crushing or yielding is going to hold, and that's going to be a constant. And it's going to be a constant that goes on forever. So that's going to be the yield stress. This is a buckling stress, and it's going to start out very high, right? If this is very low, the length is very low, then it's going to be very high. But it's going to get much smaller as L increases. And so this is the plot that we sort of look at when picking out columns. If you have a very thick, sturdy sort of column, you're going to have this control for a very long distance along this, for a long length. If you have a very slender column, that might be a nice, efficient use of material, but you're going to have this be an issue much sooner. So this diagram where we compare the stress that we're allowed on the column to the slenderness ratio is something we use quite a bit when picking out columns, particularly when we have ready-made, like rolled steel columns. Okay, so now we've determined this for a pinned column, but obviously there's other column boundary conditions that you could apply. And we've got a really great trick for dealing with that. So let's look at that in the next video.